Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Baihaki bin Baharun Syam, and the other members of my group is one Muhammad Syahmi Firdaus bin one Muhammad Zahidi. So, in this video, we will talk about the application of differentiation.
What is differentiation? Differentiation can be defined as a derivative of a function with respect to an independent variable. Differentiation in calculus can be applied to measure the function per unit change in the independent variable. When do we apply differentiation? Differentiation was applied when determining the increasing or decreasing of a function. It is also used when determining the speed or distance of moving object. Other than that, based on our topic, the derivative was used to find the maximum and minimum values of a particular function. There are 5 applied of differentiation. The first is related rates, analysis of function 1, analysis of function 2, Rolle's theorem and mean value, and applied maximum and minimum problems.
What is applied maximum and minimum problems? The process of finding maximum or minimum values called optimization. For example, maximize the profit in a company, or minimize the cost, or find the least amount of material to make a particular object. How to solve the apply maximum and minimum problems? There are 3 steps to solve the apply maximum and minimum problems. First, we need to find the derivative. Second, let the derivative equal to 0 and find the values of the variable. And the third one is we need to find the second derivative test. If second derivative is bigger than 0, it is a minimum value. But if second derivative is minus than 0, it is a maximum value. For the question 1, a farmer wants to build a rectangular pen along the side of a barn. The barn forms one side of the pen and the other 3 sides will be enclosed with the fencing. If the farmer has 100 meters of fencing material, what dimensions should the farmer use to maximize the area of the pen? So for the solution, firstly, we need to denote the width of the pen as X meters and the length of the pen as Y meters. Since the barn forms one side of the pen, the fencing required will be the sum of 3 sides, which give us the equation. The equation will be 2x plus y equal to 100. Next, we need to find the dimensions that maximize the area of the pen, which is given by the formula A equal to xy. To solve this problem, we first express the equation for the area in terms of a single variable, and then find the maximum value using differentiation. So from the equation 1, we can rewrite it as y equal to 100 minus 2x and substitute it into the area equation. So for the equation of A will be x in bracket 100 minus 2x. So the equation will be 100x minus 2x squared. After that, from the equation of A, we need to find the first derivative, which is dA over dx equal to 100x minus 2x squared. So the equation will be 100 minus 4x. To find the maximum area, we take the derivative of A with respect to x and set it equal to 0. So the solution will be dA over dx equal to 100 minus 4x. After that, we need to setting dA over dx to 0. So we have 100 minus 4x equal to 0. So after we have setting dA over dx to 0, we need to solving for x. So we get 4x equal to 100 and we get the value of x is 25. After that, we need to substitute that value of x back into the equation 1 to find the value of y. So the solution will be 2 in bracket 25 plus y equal to 100. So we get the value of y is 50. Therefore, the dimensions that maximize the area of the pen are x equal to 25 meters and y equal to 50 meters. To confirm that the dimension x equal to 25 meters and y equal to 50 meters indeed correspond to a maximum area, we can analyze the second derivative or evaluate the area at the endpoint. First, let's find the second derivative of the area function a with respect to x. So the solution will be d square a over dx squared. So we will get the negative 4. The second derivative is a constant negative 4, which indicates that the area function is concave down. Since the second derivative is negative, it confirms that the critical point we found corresponds to a maximum.
Question 2. A company wants to manufacture a cylindrical container with a fixed surface area of 400 square centimeters. What dimension should the company use to maximize the volume of the container? So let's denote the radius of the cylindrical container as r centimeters and the height of the container as h centimeters. The surface area of a cylindrical container is given by a equal to 2 pi r h plus 2 pi r square. In this case, we have a equal to 400 square centimeters. To maximize the volume of the container, we need to maximize the volume V, which is given by the formula V equal to pi r square h. We are given the constraint that the surface area is fixed at 400 square centimeters. So we can express the height h in terms of the radius r using the surface area equation, which is 400 equal to 2 pi r h plus 2 pi r square. By simplifying the equation, we get 200 equal to pi r h plus pi r square. We can rearrange this equation to express h in terms of r. h equal to open bracket 200 minus pi r square close bracket divided by pi r. Now we can express the volume V in terms of r only. V equal to pi r square h equal to pi r square in bracket 200 minus pi r square close bracket divided by pi r. By simplifying further, we have V equal to r open bracket 200 minus pi r square close bracket. To find the dimension that maximizes the volume, we'll take the derivative of V with respect to r and set it equal to 0. dv over dr equal to V equal to r in bracket 200 minus pi r square. dv over dr equal to 200 minus 3 pi r square. By setting dv over dr equal to 0, we have 200 minus 3 pi r square equal to 0. Solving for r, 3 pi r square equal to 200, r square equal to 200 divided by 3 pi. So we have r equal to 4.15 cm. Substituting this value of r back into the equation for h, we have h equal to 200 minus pi open bracket 4.15 close bracket square divided by pi times 4.15. So we have h equal to 4.15 centimeters. Therefore, the dimension that maximize the volume of the cylindrical container are a radius of approximately 4.15 cm and the height of approximately 4.15 cm. To confirm that the dimensions are equal to 4.15 cm and h equal to 4.15 cm indeed correspond to a maximum volume, we can analyze the second derivative or evaluate the volume at the endpoint. First, let's find the second derivative of the volume function v with respect to r. d square v divided by dr square equal to negative 6 pi r. The second derivative is a constant, negative 6 pi r, which indicates the volume function is concave down. Since the second derivative is negative, it confirms that the critical point we found corresponds to a maximum.
Therefore, identifying the right formula and accomplishing both first and second derivative correctly will lead to a solid answer, a maximum or a minimum cost.